Hi, we're going to talk about sinusoidal transformations. If you don't recognize kind of what the transformations are going on up here in our squared function, you may need to go back and watch some old videos, because my expectation is you know what the 2 does there, what the 4 does there, what the minus 3 does there, and what the plus 1 does there. Those are all pretty standard transformations for an x squared. And then we're going to kind of transfer that knowledge to sinusoidal, which means sine or cosine. The number out front is called the amplitude. Some vocabulary going on here. Instead of putting the 4 underneath, we actually put the number out front, and we call it the frequency. The number on the inside, the minus 3 up there, is effectively called the phase shift. That's still a horizontal shift, but because of physics, we often call it a phase shift. And then the number on the outside is still our vertical shift. So we're going to go through all those really quickly, and hopefully that'll clear some things up. So we're going to take a step back and talk about the unit circle. A badly drawn unit circle here. I've only got our numbers at 0, 90, 180, 270, and 360. Or if we're doing it in radians, at 0, pi over 2, pi, 3 pi over 2, and 2 pi. We're going to talk everything in radians here today, although you could do this in degrees. And one of the things I always like to remind my students of is cosine corresponds to the x value, and sine corresponds to the y value, and that's in alphabetical order, which makes it relatively easy to remember. So we're going to transfer those from the unit circle onto an xy graph, and we're only going to do one at a time. So we're going to do cosine of x first, and so you might have to refer back up because this is going to go off the screen. If I look at my unit circle, at 0 degrees, cosine x is at 1. And then at pi over 2, it's at 0. And then at pi, it's down at negative 1. And at 3 pi over 2, or 270 degrees, it's back at 0 again. And finally, we complete the cycle at 2 pi, and it starts repeating itself, so that it goes down again. So your cosine curve looks essentially like this. There are obviously a lot of other values that go in between. And if I was to complete some more things on my unit circle there, you would see that it does kind of make it look like a curve there more than a zigzag. I'd like to tell people it should look more like a wave than Charlie Brown's t-shirt. So that's what cosine looks like. So that's a parent function. Now the sine function looks almost identical, except it's essentially shifted over. But let's just see what that looks like real quick. So once again, you might need to go back and refer to a unit circle. But the y value at 0 degrees on the unit circle is 0. And then it goes up to 1 at pi over 2, back down to 0, then down to negative 1 at 3 pi over 2, because we're in the lower half of the graph there, back up to 0, and then finally, if I want to notice the cycle keeps repeating, it goes like this. So a very exact same looking curve, except just shifted over. And another thing that, it's helpful to memorize which of these does which. So I like to say that the cosine one here goes downhill, starts at 1 and goes downhill, so from the y-axis. And then this one starts at 0 and goes uphill. And those are also, uphill, exclamation point, extra L, goes uphill, which is also in alphabetical order. It is helpful if you know which is which, because when you start transforming these, it's helpful that you don't have to look back and forth and think, well, is that sine or is that cosine? And honestly, they can be either, but it's helpful. Sometimes it's easier to use sine or cosine based on what the function looks like when it's transformed. So we're going to do our first transformation here. We're going to say, well, what happens if I take my cosine function, and I'm going to say f of x is equal to 2 cosine x. Well, it does the exact same thing it does in all our other functions. It's just going to stretch that out in the vertical direction. So I'm going to do that with a red marker here. Okay? So my 1 would shift up basically to 2. My 0 wouldn't shift at all because 2 times 0 is 0. My negative 1 would get multiplied by 2, so it would be down at negative 2. My 0 times 2 is still a 0. My 1 times 2 is back up, and then I'm back down again. So it's the exact same curve. The zeros are all the same. It's just gotten twice as high. And that is often called, that number up front is called the amplitude. The amplitude is the distance from what's called the midline. Right here, this is called the midline. Or sometimes if we're fancy, we can call it the sinusoidal axis. But the distance from the peak down to the midline is called the amplitude, and of course the range is from the very bottom point all the way up to the top point, just as it always has been. All right, so let's do a transformation on my sine of x. So my sine of x down here, I'm going to say, well, what happens if I do g of x equals sine x plus 1? Well, that does exactly what you expect. It just takes everything here and it shifts us up. And essentially, if we want to think about it, we've got this midline here. That whole midline is going to shift up to 1. Everything's going to shift up to there. That point's a little bit off. It should really be probably right there. So that's a better one. That would look better. That wasn't a great drawing. So everything's just going to shift up. So my 0 moves up to 1. My 1 moves up to 2. My other 0 is at 1. My negative 1 is now at 0 because it's up 1. That's at 0. And then that one, if that had been drawn properly, is up 1. So exact same graph. Hasn't shifted left to right. Very quickly draw it. Looks like that. So these transformations should look familiar. Now we're going to get a little fancier. These, I think, are a little harder to see because of the wave nature. It's sometimes hard to figure out where the anchor points are. And what I like to think of is the anchor point, really, what would normally be called a vertex, is probably our sinusoidal at 0. Or our axis is where's the axis, and then where's the relative point to where our axis, what happens at the origin. So this right here, I've got drawn in here, that's the parent function, that's the sine of x. And we want to just shift that, and this is where it's always backwards. Plus pi over 2 doesn't shift it left, it actually shifts it right. So all my points are going to move to the right. So this is right. So am I saying this backwards? Plus, nope, I'm wrong. It's left pi over 2. Okay? Because the plus pi over 2 actually shifts it that way. So that point's going to shift over pi over 2. This point's going to shift pi over 2. It's going to end up here. That one's going to shift over, end up there. This one's going to shift over, end up here. This one's going to shift over, end up here. This one's going to shift over, end up here. So it's going to look like that, which, interestingly enough, looks like the cosine curve now, which is why I really can use either one of them, but usually I like to use whichever one's easiest. I don't like doing this shift if I don't have to. So that's often called a phase shift. It's really a horizontal shift, but because of physics, we often call it a phase shift. The other thing I haven't mentioned yet is the distance from 0 to 2 pi, where this cycle starts repeating, is called the period. The standard period or cycle is what probably somebody, if they didn't know the lingo, would call it. For sine and cosine is 2 pi. Unless we change it somehow, which we're going to do in the very next graph, it's going to go from 0 to 2 pi and then start repeating. Either starting at 0, ending at 0 if it's a sine, or starting at 1 and ending at 1 if it's cosine. All right, so down here I have an extended cosine curve. So this is cosine going all the way out to 4 pi. So there's one cycle or one period to there, and then there's another cycle or period to there. And the first thing I'm going to do is 2x. I'm going to do that in green. So what you might remember from other transformations is inside the function is backwards. So typically if we divide by 2, it gets twice as wide, or if we multiply by 2, it gets twice as small. So this in effect has this really compresses this. So when I do this, normally what would be at pi is now really 2 pi. When I plug pi in, cosine actually receives 2 pi. So really this point here gets compressed over to this point here, and everything's going to get compressed. So my bottommost point is half as far out, and then I've got some invisible points here. So this thing looks like this. And I got to make sure I get these in the right place. So I got a cycle and out to 2 pi. It is going to be up here again. This is going to be compressed here and here. I'm going to have another point here. Okay. And that's going to keep going. But you'll notice I got 2 cycles. When I put a 2 there, I get 2 cycles for the price of 1. And that's why this is often called the frequency. And the reason it's called the frequency is because, hold on, no battery warning, The frequency, this is how frequently, this is how frequently this happens within a standard 2 pi. So if I put a 2 out front, it'll do it twice. Well, what happens if I do it the other way? So once again, traditionally, when we put it on the inside, the number underneath is how much this thing gets multiplied by. If we write it this way, we'd probably recognize, oh, what normally was here would be twice as far out now. So for my original standard one, was 2 pi and 1, so I'm looking at the red now. That would normally go twice as far out if I divide by 2. But since we've gotten in the habit of writing it this way, we're probably going to write it this way. This is the same, but this basically says, hey, I'm only going to get half a cycle within 2 pi, which means this point here has now, my red point here, has now moved twice as far out, which is why I drew the graph so far out. So I'm going to do this in black. So this point here has now moved all the way out to here, and everything else has expanded. So like this point is twice as far out, it's going to end up, make sure I get this right, 3 pi over 2, it's going to end up at 3 pi. My pi point, which is right here, is going to end up at 2 pi, and my pi over 2 point, which was right here, is going to end up there. And this is 0, so it doesn't change. So now this thing is same thing, just twice as wide. Okay, that takes a little wrapping your head around it, as well as I think it always has. But the big change here is we're probably going to write this as a number out front now, as opposed to a number underneath. So we're either going to express it as an integer, which means it compresses it, and that's how many cycles I have within 2 pi, or I write it as a fraction out front, and that's still how many cycles I have, but effectively it stretches it out. Okay, got 2 quick problems for you here. I've talked a little longer than I wanted to. My battery's probably going to run out. First one. Take a look at this. See if you can graph it. You might want to stop it, and then I'm going to very quickly do it. So my axis has moved up 1. So what was here? I'm going to do this in black. What was here at 0 has moved up to 1, so this is now my new axis, so everything's going to go around the point. The negative is going to flip it, so instead of being 1 above, I'm going to be 1 below, because cosine would normally be 1 above the axis, but now I'm going to be 1 below the axis, but it's also times 3. So I'm going to flip it and then down 1, 2, 3, and this point right here, which is on the axis, is still going to be on the axis. This point right here, which was 1 below the axis, instead of being 1 below the axis, it's going to be 1 above the axis, but times 3, 1, 2, 3, roughly here. This point here is still on the axis, and this point, which was 1 above the axis, it's flipped, but then 1, 2, 3, it's going to end up right down there. So this ends up looking something like that. So my axis points have not moved, other than the axis moved up. But then my points above and below the axis have flipped because of the negative, and then they're 3 times as far as they normally would be. So that's 3 times as far, so 3 more. It's 1 times 3 is 3 down, and 1 times 3 is 3 up. Okay, this is going on a bit long. Last one. Doing it in reverse. Here's a picture. Can you tell, and this is a hard one, can you tell what's happened here? Can you write the equation? All right, so I've got my sine is my parent function down here, and there's some notes here. I've got these by 1, 2, 3, 4, 5, 6, so pi over 2 is there, pi is there, 3 pi over 2 is there, 2 pi is there. And I've got some notes. It's like, oh, this point that was here has moved over by 1, and this point that was here has moved over by 1. So I'm doing a phase shift that's definitely moved, and also you can probably tell, oh, it looks like the sinusoidal axis has moved. It has. My sinusoidal axis is right there. So that's I know what's happened there. This is definitely some kind of thing, plus 1. So y equals something plus 1. I started with sine, so that's a hint. I could use cosine to figure this out, but it's probably sine that's been moved over by 1. So sine, it's moved over by 1, and then this is where it's backwards. This is x minus 1, because this point here has shifted over and up 1. So that's where that point moved to. It moved over and up in the same way that this point right here, has moved over and up 1. So there's my shift, there's my shift. And if there's more than one thing going on there, it can get very complicated. All right, that's probably way too long. Thanks for watching. Ciao.